Okay, hi everyone. We're gonna get started. So yeah, remember that homework 2 is due tonight at midnight, and project 1 was originally scheduled to be released today, but we're gonna push it back a week. So it'll be released next Thursday, and you'll have 2 weeks to do that. So you have plenty of time. Don't worry. So yeah, enjoy your little 1 week break. Okay, so today we're gonna talk about linear regression, and linear regression might seem like pretty simple or easy. But there's actually a lot to unpack in here, and I think you'll think it's pretty cool, as I do. Okay. So today's agenda, we're just gonna have a little background about what regression is, what is linear regression, and then we're gonna tackle linear regression from 3 different perspectives. One using linear algebra, one we're gonna optimize it using gradient descent, which I'll talk about, and another probabilistic perspective. And my hope is by doing this, you'll be able to see linear regression and its potential in 3 different ways, and hopefully, that'll be something cool for you guys. Also, can everyone hear me? Like, put your thumbs down if you can't. Okay, awesome. Sweet. Okay, so some background. So last time we talked about the 3 different types of learning. There's supervised, unsupervised, and reinforcement learning. So we have a chart up here. It excludes reinforcement learning, but that's okay. So it really breaks down supervised and unsupervised learning in two aspects, continuous and discrete. So in supervised learning, we have our label data. We have our data with some labels. So either if they're discrete labels, like dog, cat, fish, we can classify them. If they're continuous, we might want to regress over them. So for example, if I'm given a bunch of data about student ages, and I want to predict what their height would be, that would be continuous because height is a continuous variable. Same thing for unsupervised. If we're in the continuous case, we do something called dimensionality reduction, where we want to take our input data and express it in the most compact ways possible. And this kind of allows us to learn better features or learn the most important parts of our data. And similarly, we have something in the discrete case called clustering. You guys might have heard of k-means or something similar. So today we'll be tackling regression, and specifically linear regression. So this is the setup. We want to model these relationships and make predictions, right? We have our data, and we have what the label is, right? So in our linear regression case, in the continuous and supervised case, our data has continuous labels y. So for example, this could be prices, heights, MPG, etc. And our data also has explanatory variables xi. So xi is what we use to predict these labels. So for example, sales, weights, engine power. So engine power can predict, MPG, and weights can predict height, sales can predict prices, etc. So in linear regression, we have a bunch of these xi's, and we want to predict the y from these xi's. And that's what we're going to explore today. So yeah, how does a computer make predictions based off of this? That's our topic for today. So regression is one of the most commonly used methods of data scientists, and the reason is because it's very simple and it's really, really powerful. There's a bunch of things you can do with it. They're widely used in a bunch of stuff. For example, in physics, Ohm's law, Hooke's law, Charles' law. Have any of you guys heard of these laws? They're pretty common, right? This is all based on regression. And same in econ, if you've heard of Okun's law, same thing. So it's really cheap and it's really practical. That's why a lot of people use it. So yeah, this is what linear regression looks like. You have a bunch of points, and you think that there's some sort of linear trend in your data. Your data goes in some linear fashion. So basically what this blue line is it's trying to best find this linear trend in your data. So the way it does it is by using these lines. So does anyone know exactly how this line is calculated, or what measure we use to calculate this line? Yeah, your hand.
The sum of the squared.
Exactly, yeah, and your name? Noah, all right. So Noah said it's the sum of the squared distances between the point and each line. And yeah, he's exactly right. This line, this is the best line. This is the line that minimizes the sum of these squared distances. And we'll kind of see why that's important and how that plays a role. So yeah, the topic of today will be how do we come up with that best fitting line to be able to understand our data. So this is our setup, right? Suppose we have these p predictor variables. Remember, the x's are our predictors. That's our input data, and we want to predict y out of those. So we have p of these predictor variables. So in linear regression, we predict our y out of a linear combination of these p predictor variables. What a linear combination means is that we have a coefficient in front of each of these predictor variables, and those coefficients are only to the first power. They only have to the degree 1. So does this make sense? So for each predictor variable, you have a coefficient, and then you have this extra term out here. This is typically called the bias, but this is just you can think of it as like a y-intercept. That's basically what it is. Does anyone have questions on this part? Okay. Oh yeah.
Is there like a name for that? H of X function?
Yeah. So this is just some notation. This basically means our model. So h is like our prediction, and it's determined by our weights theta. So our model is determined by these coefficients. So this is just some fancy notation we use to refer to it that way. Yep.
Do the variables also have an associated degree, like degree 1, just like the coefficients do?
Right, yeah, good question, and you're actually quite a bit ahead of me there, but yeah. So for now, we're going to assume that these variables only have degree 1. But later later today we'll explore what happens when these become higher degrees. Yep. Okay. So here the thetas are our parameters, and they're called our weights. So that's what determine our model, right? So our model is basically taking in a bunch of these x's and predicting a y. So we need to determine these thetas. And so basically our job is to estimate the thetas that would make this best model. So anyone heard of anyone seen this matrix or vector notation? Is everyone familiar with that? If you're not familiar with that, all that means is that you take all these x's and you just stack it up. And you do the same thing for the thetas, you just stack it up. And this basically means your dot product between them two. So you do a pairwise multiplication between each element, and then you sum them up. So here, this is the same thing as taking a pairwise multiplication of each of the I indices and then summing them up. That's the same thing as this theta t x over here. Yeah, so also, if you notice, we have this one bias term. What we can do is in the x vector, we can stack an extra 1 at the bottom. That way we can get this bias term to appear. Yep. Yeah, I equals 0, you're right. Yeah, because you have p predictor variables. Yeah, you're right. Yeah. Okay, so to make that a little more clear, right? Suppose we have this following data. We have the price of each house, the number of square feet the house has, and the number of bedrooms. So we want to predict the price of a house just from the number of square feet. So for now, let's ignore the number of bedrooms. So can anyone tell me what our model will look like in that case? Which coefficients we would have? Anyone want to make a guess? No? Okay, pretty silent audience. All right. So, so our linear model has this form, right? So our data is just one explanatory variable, the square feet, and we have one coefficient for square feet, and then a bias term, and that's our model. So a brief recap of what we just covered. We're given labeled data in x, y pairs, right? Remember that we could have many predictor variables for a single, for every data point. We can construct our model. We know what our model looks like, right? We know we have a bunch of these coefficients and a bias term to predict this y. So now there's still things we need to do. We still need to figure out how close is our prediction to y, right? How do we estimate that? And once we know how close it is, how can we optimize it so that it's even closer to y? And then find the minimum from there. Okay, so to solve this problem, one way to do it is through linear algebra. So this might get a little mathy. Don't worry if you're a bit lost on the concepts. Please ask for questions, and you can also come talk to me afterwards if you have any questions. Yeah. So our goal, we want h theta of x to be as close to y as possible. Remember, y is our label data, and h theta is our prediction. So someone here said that we want to measure how different each prediction is via squared error, right? So we can express this mathematically. So we're looping over all our data points, and we're going to take our prediction, right? This is h theta of xi. Xi is that one data point. We're going to take this, and then we're going to find the difference between our prediction and what it really was, and square it, and then sum all those up. So typically we refer to L of theta. This notation here is our loss. That's our loss term. That's how far away we are from our actual goal. So here we sum up the squared residuals. And to have an accurate model, we really want to minimize the loss. Because what does it mean if the loss is 0? That means for each data point, my prediction was exactly what the label was. So that'll be like a perfect model, right? So in the general sense, we want to minimize this loss. Anyone have any questions here? Yep.
Do we square it just to make it positive?
Yeah, good question. We'll talk about that in the third section about probabilistic perspective. We'll talk about why this squaring is important. But yeah, typically you want it to be positive, so some things you can do is to just have an absolute value. But yeah, we'll talk more about this. Any other questions? Okay. Okay, so now we're going to try and put this in a matrix notation. So recall this is our loss, right? So this is the same thing as, now we can just substitute it. This is our model, right? So our model is just this dot product between our coefficients and the data point. And I'm just flipping it around for easier notation, but since it's squared, it's the same thing, right? The negative sign doesn't matter. We can rewrite this as this thing. So this is just a scalar. It's a singular value. This dot product returns a scalar. This is a scalar. So squaring it is the same thing as taking this 2 norm, which is referred to as the Euclidean distance, if anyone knows. So the Euclidean distance of a scalar is just, the scalar squared. So nothing special here. But this allows us to put it into matrix notation, which is this. So typically, this is how you'll see the loss for a linear regression expressed. Basically, each row of x is a data point. So what we're doing here is we're taking each row of x and then multiplying it with our coefficients, and that'll give us the first y. And then doing it with the second one to get the second one. And then finally, we'll have this vector of like residuals, and we're just going to square each term and add it all up. That's what this L2 norm here means. Okay, don't worry if you don't understand this. Just make sure like this kind of makes sense. Yep.
Just theta just our coefficients.
Yeah, theta are our coefficients. Yep. Okay. To look at it from another perspective, right? This is our equation for the linear model. The outcome, right, can be thought of as our prediction plus some error. So our prediction is not always going to match the true label. So there's always going to be some error here, unless your data is perfectly linear. So we can model this error, right? So we don't know what the true theta is, but we want to estimate it. So our predictions will be like this y hat. So every time we have a prediction, we'll refer to it as a y hat, or a theta h, or a theta hat, or h theta hat. So we can rewrite this in terms of this like matrix, right? This is basically what I showed before. You take your thetas and you multiply with this first row of x's, and you get that first y with that error term. And you do the same thing for the second row of x's. You multiply the second row of x's with this with your coefficients, and you get that second y term. Does this make more sense now? It's like the same matrix notation that I showed you before. Okay, cool. So yeah, in the matrix notation, this is what it is. So yeah, we're going to use capital letters to represent matrices and arrows to represent vectors. Yep.
What is the E vector?
That's the error. So when we make a prediction, we're not going to be exact to y, right? So we can't just set this equal to y because that doesn't make sense. So we have this vector of errors called E that will help offset that.
And we want to minimize E.
Right, exactly. Or yeah, we want to minimize it. Okay, so we want our estimate to be accurate. So we can be accurate by trying to minimize error. So one thing we can do is just, subtract it to the other side. Now we get this is the error. So, the question asked here is why can't we just use something like this, instead of like why do we square it? But it's more mathematically convenient to minimize the square residuals. If you know, like, basically, if I square this and I take the derivative of it, it's a lot easier than to take the derivative of this without the square. And there are a few other probabilistic reasons why we do that. So just like trust me, and like this is like one of the more standard ways to do it for now, and we'll explore more why about that later on. But does this make sense to everyone? Does it make sense, this notation and the loss? Any questions on that? Okay, cool. So it turns out that if you look at this, right, basically what this is doing is that for your x, for your data row at x, these thetas are providing some sort of linear combination of that, right? That's what linear regression is. For your data point, you're getting the linear combination, and then you're seeing how close it is to your y. So you can think of it as in this like geometric perspective, right? You have this x, which is like your data field, and then your x theta is providing all linear combinations of it. And your y vector is somewhere outside of the data field. You're basically trying to minimize how far your projection of that y vector is onto your data field. So if you look at it this way, right? Here's the column space of x, which is basically like your data field. Here we use this picture is the b, but this is the same thing as theta, right? So we use some linear combination of the weights to get here. So y is actually a vector going all the way there. But we only operate on this data field because we're only a linear combination of the elements in this data field. So how do we get as close to y as possible while remaining on the data field? Does anyone know? Yeah, no. Exactly, right? You just project y down onto this, onto the column space of x. Does everyone see like kind of why that is? You just project it down, right? Yep.
So it's going to be the vector x, right?
Yeah. With these like optimal weights. Yep. Okay, so mathematically, if anyone, your question up there?
Is it just like the component of the y vector, or is it like if you were to like push it down?
It's like if you were to, basically like if you were to, if there was like a, think of it as if there was a sun all the way up there, and it's just shining down. It's like a shadow, right? Yeah. So like how far this y vector travels in this like, if you think of it as a triangle, like this x direction and then this like y direction, like the length of this vector would be like this x direction. Yeah. Yep.
So is the x beta hat then like our prediction?
Exactly, right? That's the best model we can get.
So would the like residuals y minus y hat always be orthogonal to the column space?
Yep, exactly, right? Because if it wasn't, that means there'd be still room for us to include more elements of the column space of x.
If it was like a perfect prediction, then would y just lie in that?
Yeah. If our data was perfectly linear, then y would be in the column space of x. Okay, cool. So mathematically, we can express this as this, right? If anyone knows how to take a projection, I'm not going to go through the math right now, but I'll post some links afterwards. That's if you just take the projection, basically theta and the optimal weights end up being that. You know, if you ask anyone like what's like the standard OLS formula, that's that xdx inverse xty. And that's like the closed form solution. So what this means is that given our x and y, we use this formula, bam, we're good to go. We've got like our optimal weights. Now, I know that was a little bit hand wavy, so if you guys want some, there's like another way to look at this, and that's kind of this way. So don't worry about this. I don't expect you guys to know this, but we're trying to minimize this loss, right? What does this 2 norm squared mean? We can just, like vector calculus, that's simply the dot product of that vector with itself, and we can expand it out. And now we're trying to minimize this function, right? So what are we trying to do? How do you minimize a function? This is like calculus, if anyone's familiar with that, right? You just take the derivative and set it equal to 0. So I take the derivative with respect to this vector theta, and I get this. Set it equal to 0 and I solve for it and I get that. So, if anyone's interested. Okay, cool. So, a bit of interpretation of our model, right? So theta is indeed our minimizer, because if you take the second derivative, you'll see that it's negative. So what does that mean? That it minimizes this function, this loss function. So now, once we have our theta hat, our estimates, we can perform new predictions by just using these coefficients to, multiply by our predictor variables and get our estimate for y hat. Does anyone have a question on this part? Yep.
Wait, shouldn't the second derivative be positive because your slope is increasing?
Second derivative.
It's like a valid.
Yeah, you're right. Yeah. Okay. So in matrix notation, if we wanted to perform a prediction, So our weights are our weights are xtx inverse xty, and if we want to perform a prediction, we just multiply by x on the right side. Because that was our loss formulation. Remember, y minus x theta hat. So to perform new predictions, we just use this. Does this make sense to everyone? Okay, cool. What this really means is that, like, if we increased our predictor variables by 1 unit, since this is just scaling each of those predictor variables by theta p, for example, if we increase xip by 1 unit, then we expect our estimate to increase by theta p. Does that make sense to everyone? So, like, perturbing our data point by like 1 would cause our prediction to change by theta p, for example. Yeah.
Is that because it's linear?
Yeah, that's because it's linear. So just a little bit of like how to interpret the model. Okay. So does anyone have any questions on any of this part before I move to the next part? Okay. Okay, cool. So a second perspective we can look at it is by optimizing via gradient descent. So don't worry what that means. I'll get to it. So again, we have our h theta of x. We want it to be as close to y as possible. So we know how to do this by solving some equations. But now let's look at a more general purpose way to solve it. Let's look at a general purpose algorithm that can be used to solve this problem. Not only this problem, but a lot of other problems as well. And you know, it turns out it's used a lot in when we train neural networks. So yeah, it's very important. And it allows us to optimize a lot more complex models than just this one linear regression. So this is our cost function. We put the 1/2 here just because when we take the derivative of this, it cancels out and it's like nice. So, okay, any questions? This really doesn't matter when you're trying to minimize this because it doesn't depend on theta. Okay, so yeah, sum discovered residuals, and we want to minimize our loss. So the idea is to choose a random theta. And then we choose a random theta, and we take some step in a direction that we think is going to be better. We're going to change theta a little bit so that it's a little better. And then we're going to change theta a little bit again so it's a little better again. So we have an initial guess. We repeatedly update it to make our loss smaller. And we keep doing this until it doesn't change anymore, until we've reached a minimum. So if you think about it, if suppose this is our trajectory, right? We change it a little bit in a direction that we think is going to make it smaller. And we change it again. And we keep changing our thetas incrementally until we get to a minimum. And we can't, there's no direction that we can change it anymore that would minimize this loss. Does this kind of general idea make sense? Don't worry about how to find that place to change it to. Yeah, so basically we have gradient descent is this like iterative algorithm where you have an initial starting point and then you change your point a little bit to where you think it'll be closer to the minimum, and you keep doing this again and again. So just a note, our loss is a convex quadratic function, which means it has nice properties when taking derivatives and taking gradients and so forth. So from Math 53, right, we know that the direction of greatest increase is the same direction as the gradient vector. Basically, this means that if you take the gradient of a function, the gradient, the way we can go to the place where the function is the maximum, is by following that gradient. Does anyone have any questions on that? Okay. So, right, so the gradient vector will get you to the max, but we really want to find the min. So why don't we just go in the opposite direction? And so that's what gradient descent is, right? We take the gradient, and that'll tell us, like, around my local area, where's approximately the max? Where's the function increasing? And then we just negate that to find, where's the function decreasing? So this scheme is kind of known as gradient descent. So what this really is we have our initial theta, we're going to take the gradient of the loss with respect to theta. That's our gradient. Once we take this gradient, we know the direction that we can go that will maximize this function. So we want to negate it in order to find the direction that we go to minimize this function. So now this gradient basically is telling us how much do we change and in what direction in order to get to the minimum. And typically we multiply it by this epsilon, which is called the learning rate. It's like a small constant, like a lot of times like 0.001. So that ensures we take like small steps at a time. So our new theta will just be the old theta minus the direction of the gradient. Does anyone have any questions on that? Oh, yeah.
Is there like a way in general to optimize both the speed that you're towards that and how small the steps are so that you're accurate?
Yeah, this is actually like a very active field of research. Like, what's the best way to like optimize, optimize our cost function? So you could have like a constant steps learning rate. You could change it over some time. Like, you have it at like 0.001, and then you have it like every few periods or so. You could use more complex methods instead of just using the gradient. You could use second order derivatives like the Hessian to better approximate like your curvature or something like that. So yeah, like definitely there's like a lot to do here. This is like very simple. Okay. So epsilon is called the learning rate. So this is like a visualization, right? So this is our cost function. This is the landscape of our cost function. And we can think of this as the model space or our theta space, right? So for example, if we have two coefficients, two weights, one axis would be theta 1 and the other axis would be theta 2. And this kind of curvature shows us where the loss is the minimum. So if we start at some random point over there, we would take the gradient with respect to the cost function at that point. And we'd find that going that way would increase, would be the direction of the gradient. So we just take it a step in the opposite direction. And we keep doing that repetitively. And what you know is like, when you get to a minimum, the derivative at that point is 0. So your slope is 0. So what happens is that as you get closer and closer to the minimum, your gradient becomes smaller and smaller. So what that means is that the steps you'll take become smaller and smaller. And eventually you converge to the minimum right here. Does this visualization make sense? Yep.
What if your L function wasn't convex? Could you get caught in like a local minimum?
Yeah, that's true. So that is very true. So yeah, gradient descent is like typically kind of hard to work with. And yeah, if your cost function is not convex, then you will get caught in like local minima, and it's like very likely. But yeah, so yeah, it's always like if it's like convex, then you know that you can like reach this minimum for sure, because there's only like one point at where the gradient is 0. Yep. Okay, cool. So just to start off like with a simple example, right? You don't have to worry about all this math, but suppose we want to train our model, and we only have one training example, x, y. This is our only training point, right? So what we do first is the gradient with respect to our loss, we're just substituting in what our loss is here, right? So it's just this equation. Does this first line make sense to everyone? The gradient of our loss is just the gradient of this our cost function. Okay, and now here, we're just using chain rule. So the derivative of this function, right? We bring the exponent down, and then the gradient of the function inside. Does this second line make sense? Any questions here?
Why don't we just take the derivative?
Pardon?
Why don't we take the derivative?
Oh yeah. Well, why do we take the gradient?
Or you just said we took the derivative, right?
Oh, yeah, gradient, derivative, like kind of interchangeable, but gradient is just like a derivative in like multiple dimensions. Yeah. So yeah, here basically you can think of it as like as a derivative, basically. Yeah. Okay, so now that we're here, this 2 and this 1/2 cancels out, right? Which is kind of nice. We wanted that. So we have this, and now we're just substituting in what our model is here in this third line, right? Our model is just this dot product. Does that make sense to everyone? Does everyone follow to this third line? Okay, cool. And oh yeah, questions?
So taking the gradient with respect to theta.
Yeah, with respect to theta. Okay, and now from this third line, this is a bit of vector calculus, but basically this part is the gradient with respect to this minus the gradient with respect to this. Y doesn't depend on theta, so it's kind of like taking the derivative of y with respect to x. You know, it doesn't make sense. It's just 0. So this just goes to 0, and the gradient with respect to theta of theta tx is just x. So that's kind of like if you had a function ax and you took the derivative with respect to x, that would be a. So it's the same thing here, but we get, yeah, basically the same thing here. This transpose is just like something that pops out of doing like vector calculus, but you don't need to worry about that. So does anyone have any questions on this? How we derive this gradient descent update rule? Yeah, I know that this can get pretty complex, so yeah, like don't feel free to ask any questions that you have. Yep.
The theta is like the slope of the cost function,
The theta.
right? Theta is
So theta are our model parameters.
it's like in the linear combination. So
Yeah, exactly. Yeah. So for the linear regression case, we figured out basically what our gradient is with respect to theta. So now that we have this gradient, we can just plug it into our formula, right? So we have our new theta, just our old theta minus the learning rate times what we found here. And I'm just using this one notation to refer to, like, you know, for a single training example. But typically, if you have multiple training examples, all you do is find the loss for all of them, or the gradient for all of them, and then average it out. Does that make sense? It's just nothing but an average here. Any questions on, yeah?
why did you flip it around?
Flip what part
Why
around?
did you line minus c?
We will always use an h minus y and then.
Ooh, yeah. Sorry, bit of messed up notation there. You're right. It should be h minus y. Yep. Okay, so if we have multiple training examples, right? What we do is we have this loss function. We just sum it up all overall all n. And typically, you know, our learning rate can include like a normalization factor for the number of training examples that we have. So it becomes more like an average. So here, the notation, if it's in the superscript, that refers to like the training example, like which data point. And j here refers to the index. So for example, theta j is the jth index in the theta vector. So that's like, for example, like theta p or example, something like that. So that's theta j. So for this is basically saying each coordinate of theta. So basically, we just use this and we find that same jth coordinate of our x over here, and then we use that to update it. And you know, we do this across all our coordinates and all our data points. Yep.
So that's saying like all the ways to train with all of the data?
Yeah. So for now, we're formulating it as that. There are things called like batches. So you can, you know, split your data into batches and then do one step on one batch and another step on another batch. But yeah, this is just like a general form. Okay, cool. So this rule is also called like the least mean squares rule. It's not really important. So yeah, a key thing to note is that the size of our update is proportional to the residual term. So our residual term is this, remember? So the size of our update is proportional to that. So how much ever we are off by, that much it changes. So the closer and closer we get to our true target, the smaller and smaller our steps become, even if our learning rate is constant. And that's like the key fact, because the closer and closer we get to the minimum, the slower and slower we want to go so we can accurately find it. Otherwise, we can just keep bouncing around everywhere, which I'll show in a second. Yep.
Is there like some threshold that is defined? So
Yeah, typically you'd say like, oh, sometimes you can say like, oh, if the gradient is like so small, then stop, because that means you probably reached a minimum. Or you can say if my loss hasn't changed, or if my loss hasn't changed by like some tolerance, then stop. Yep. Any other questions? Okay, cool. Yeah, basically if our prediction is close to the actual y, then our parameters shouldn't need much changing, and so they don't. So basically, so we talked about gradient descent. Now there's this other term called stochastic gradient descent, or SGD, that you guys might have heard. And the idea is basically we can use all our data to estimate, one step that we take in our algorithm. For example, here, this big step, we can use all our data to estimate this one step. But that turns out to be very costly a lot of the times, using all your data to compute this one step and doing it over and over again for thousands of iterations. So instead what you can do is just use, for example, a few examples, or even just one example to compute this step, and then do it again and again. And the idea is that one example will still provide you a good estimate of where your minimum is. And that way you don't need to keep recomputing across all your data samples all over again. And it's also real important because it won't be near the true minimum. So it'll provide this noisy estimate of where the true minimum is. And that'll act as sort of like a regularizer, which we'll talk about next week. So in stochastic gradient descent, what we do is for each data point, we will update all the coordinates of our model. And then we'll go to the next data point. And then we'll update all the coordinates again. And then we'll do that again and again. So SGD is a very popular algorithm because it requires less computational time than gradient descent typically. Because the intuition is that if you're far away from the minimum, you don't need that many points to know approximately where your minimum is. You don't need to have a super accurate estimate. You just need to take a step in the general direction. And as you get closer and closer, your update steps will get smaller and smaller anyway. So, low chance of you overshooting. Does this kind of make sense? Any questions? Okay. Yeah, so as I talked about, choosing a learning rate, right? So, for example, if we have too big of a learning rate, we can start to overshoot. So for example, we start here, and then suppose our next step in our gradient descent takes us over here. So what is our optimization algorithm thinking right now? I took a step, and it turned out, it decreased my loss function pretty well. So I was like, okay, I'm on the right track, I'm doing pretty good. So we'll take pretty much the same size step, or a big step, in the same direction. And if our learning rate is too big, then it could just go back to the other side of the parabola and overshoot. And we can just keep going up and up, and just rattle off, And that's a bad thing. We don't want that to happen. One sec, let me just finish this and I'll get to your question. On the other hand, if we have too small of a learning rate, we can take really, really small steps, and then we'll get stuck in a local minimum. For example, as you pointed out, if our function is not convex, we can get stuck in a local minimum. And even if our function is convex, if our learning rate converges too quickly, we could get stuck in a non-optimal position. So we typically want to find the right balance between a large learning rate and a small learning rate for gradient descent. Yep, question?
So what's the difference between just regular gradient descent and stochastic gradient descent?
Right, so in regular gradient descent, when we update each coordinate of our model, we use all of our data points, all of our training points. So we take the gradient with respect to all of our training points, average them out. Now we have this gradient vector, and then we update our model. That's one step. Then the next step, we again use the gradient across all the training points, and then update our model. In stochastic gradient descent, we use one training point, update our model. That's one step. Then use another training point to update our model. That's a second step. And so on. And stochastic gradient descent doesn't have to be just one training point. You could use a batch, 50 or 100 or something like that. But yeah, typically it's fairly small compared to the data set. Does that answer your question?
Yeah.
Okay, cool. So any other questions on anything so far? Oh, yeah?
Minimizing data, is there an issue of overfitting?
Yeah, so there is an issue. And so linear regression typically doesn't overfit because, or has a really low chance of overfitting because it's a very, it's not a very expressive model. There's not many ways it could go wrong. But for example, if you're training like a really huge network, then yes, overfitting does become a very important issue. And we'll talk about in the future lectures like what overfitting is and how to go about like stopping it or mitigating its effects. Okay, so yeah, SGD or stochastic gradient descent is the basis for like a lot of optimization algorithms. So as you saw, it's not necessary for linear regression because we saw a closed form solution where you can just plug in some numbers and you'll get out the right answer. But it's really easy to kind of understand what SGD is doing in the linear regression case because it's so simple. And so yeah, we use the derivatives to calculate them, and it's pretty easy. And it's really useful when we have derivatives but no closed form solution. So in like big neural nets, for example, we have a lot of derivatives. We can take a lot of derivatives, but there's no closed form solution. So yeah, we get the equations that I showed before for like the exact solution are called normal equations, in case anyone's wondering. Okay, yeah.
What's a closed form solution?
Basically like okay, like something like this. Like closed form solution just means like it's one formula. You can plug everything into there and you'll get out your answer. So closed form is like closed. Like there's nothing extra need to be done. Like it's like there's like this one formula. You put everything in, and there you go, right? So that's like what this is. You have your x and your y. You just put everything into the formula, and then you get out your predictions. Gradient descent, right? There's no like closed form solution. You have to keep doing this iteratively again and again and again. Yeah. There's like basically no succinct way to represent like what your optimum is. Okay. Oh yeah, so just to recap, right? So we're looking at linear regression, and we've looked at it two ways so far. One, how to solve it directly using some linear algebra and some vector calculus, and the second, using gradient descent to optimize it. So these are both two ways in which we can optimize linear regression or solve for the right model parameters in a linear regression case. Now we're going to look at kind of how to reason about linear regression and where its roots come from and why we use that squared law explicitly. So this would be like a little bit of a different direction. We're not going to be talking about optimizing the cost function. So any questions before I move on? Is that a hand back there? Oh, okay, you're just stretching. All right. Okay, so yeah, regression is a really good summary of data. But this kind of assumes that our data has some key properties. So we need to know, in order to be intelligent data scientists, we need to know what these assumptions are, where they come from, and when or why they can fall apart. So the first assumption is linearity. We're assuming that our data is linear. If we try to fit a line to a parabola, it's not going to work, right? It's because our data is inherently second order in degree, when we assume that it was first order when trying to fit a linear regression model. Normality of errors, meaning that each error is normally distributed. So does anyone know what the normal distribution is? Yeah, it's like a bell curve, right? So it's just like this, right? It's like a distribution that kind of looks like this. And it's like a really popular distribution because it can explain a lot of random processes in life and a lot of data with this like kind of normal distribution. So when we say normality of errors, we mean that, for example, when we had that y equals x theta plus e, that error term, we were assuming that each error was kind of like normally distributed. And we'll talk a little bit more about what that means. But any questions so far? Okay. There's another thing called homoscedasticity, which is constant variance. So a normal distribution is parameterized by its mean and its variance. So the mean is like kind of the average of where it is, and the variance is how spread out it is. So here, each of the errors, we assume them to have 0 mean, but like some sort of variance, right? When we say constant variance, we're basically saying that each error term, each error coordinate has the same variance. So whatever this is, it's the same across all of them. So we're assuming that each of our errors have the exact same normal distribution. 0 mean and this one variance term. So they have the exact same shape. And we'll talk about why we make this assumption. And the last one is independence of errors, that each error is independent of the other one. Or in other words, that they're perpendicular to each other. Okay, so when we do linear regression, right, we're basically using this data that we've observed and collected. So in the real world, right, there's some natural processes. These processes make this data that we collect and observe. So what we are trying to do is we are trying to build a model that mimics the real world model as close as possible. So the real world has some model. It takes in some explanatory variables and spits out some labels. We observe what these explanatory variables and these labels are, and we're trying to recreate what this model is that the real world uses, because we don't know that model. So the problem is that there are some factors that we can directly observe and that others that we can't. So when we observe the explanatory variables and our labels, there might be some noise in them. And we can't directly tell what the model is. And yeah, another problem is we don't know what model the world uses, right? Okay. So in order to reason about this process more rigorously, let's kind of construct a toy universe in which to analyze our models. So, we get our data from the real world, but just for the purposes of the next 30 minutes, we're going to go into a toy universe where we can kind of, we can define the data generation process, and that'll allow us to better analyze what's happening. Does everyone follow with me so far? Okay. So, suppose in our toy universe, the data is generated through this linear model. Right? So we're talking about linear models. Let's talk about this linear model. Okay. So our toy universe creates this data somehow through some process. So what we observe the y values, and we observe the x, but our observations have some noise in them. We can't directly observe these x and the y, and the x and the y. Our observations have some noise. We're limited in some capacity. So how do we represent this? We represent this by our linear model x theta plus z, where z is some normal distribution. So what this means is that if we didn't have the z, this model would be the exact same. Everything is determined by this, right? When we add in the z, we're adding a little bit of noise. We're shifting the measurements ever so slightly in this direction with this normal distribution. Anyone confused on this normal distribution here? Please ask me. It can be tough to get your head around at first. It's basically like saying we have this normal distribution and we're going to pluck out small values from it. Typically this variance is very small and mean of 0. And we're going to perturb our data a little bit. So it has a little bit of noise, a little bit of error in it. So we can represent our model that way. So yeah, this is kind of like what these are what a bunch of normal distributions look like. So for example, this one is not 0 mean, but all these three are. So this orange one here has a really large variance because its spread is really big. This blue one here has a really small variance because its spread is really small. So yeah, typically these variances are really small in our errors. So they look something like this. So if you assume that all our data lies on this line over here, we're just going to perturb it ever so slightly along this normal distribution. Ever so slightly. So basically now, this data won't be linear anymore in x, right? Our y's won't be exactly linear. They'll have some disturbance to it. Okay, so we have this noisy data. right, that we've observed. And we want to find the theta that can best replicate what we already observed, right, the data we've observed. We want to find the theta that best replicates the real-world model, which is the real theta, right? And the real theta created the data. So we're trying to find the theta that best replicates the data that we've seen. Because if we can find a way to efficiently well replicate the data that we see, that means we've like found a good approximation to a real-world model. So in other words, we want to increase the likelihood of the observed data coming from our model, right? If our model was something that takes in these x's and produces these y's, we want to increase the likelihood of creating good y's, right? That's what we want to optimize the theta to be. Is anyone confused here? Okay. So let's unpack what increase the likelihood means, right? So let's look a little bit about notation. So really, what this is saying is that we have our model, and we have a bunch of explanatory variables or data points, and we want to find the theta that best gives us the probability of these labels. So this is like conditional probability, but what this is basically saying is that given a model in our x, right, we want something that can give us the highest likelihood of y. And we're going to be maximizing over our theta, right? So what we're saying is we're going to be shifting our theta such that for a given theta in an x, our labels, our y's, are the most likely, or have the greatest probability. And we're doing this for all our data samples. So given our model, and given all these explanatory variables for our data samples, we want to maximize the probability of seeing these outcomes, these y outcomes. Does this make sense to everyone? Okay, cool. So we have this, right? This is what's called like a maximum likelihood estimate. You don't need to worry about that. And you don't need to worry about any of the math I'm going to do right now. This is just like a quick derivation to show of why some of the assumptions in linear regression hold. Okay, so we have this, right? And what we know is that each data point is generated independently. So each x and y are conditionally independent. So what that means is that we can rewrite that as this. So it's just the product of all the probabilities for each data point, right? So this here is saying is that given a theta and an x, we want to maximize the probability of seeing that x's label. And we're going to multiply all these probabilities together, right? Like it's like flipping a coin. Like what's the probability that you get two heads, right? So the probability that you get one head times the probability you get another head. Same thing here. What's the probability to see that your sample is likely? All your samples are likely. Is the probability that your first sample is likely times the probability that your second sample is likely, etc. So now we try to maximize this, right? And if anyone knows like what the log function is, right? It's basically like it just looks like this, and it's like always increasing. So we can take the log of this to get this. So what this means is that we can take the log of this function. So we get the log of the product of a bunch of these. And what's the log of a product of something? Is just the sum of the log of those things, right? So we can break it up like this and sum it this way. Yeah. Is anyone confused? Anyone have any questions? Yep.
So what are the assumptions that we make on x and y? It's like, is it just that they're conditionally independent, or?
Yeah. So we assume that they're like generated independently. So yeah, that's what allows us to break up that into that. Yep.
What's the intuition behind just taking the log?
Oh, just to make this to turn it from a product into summation. Because the log doesn't do anything, right? Maximizing the log will still maximize the original function because log is monotonically increasing. So this is just to get into a nice sum. Yeah. Okay. So now if we go back to the previous slide, right? You'll remember that our y's were generated with this process. So this noise had 0 mean with some variance. So when we add it to this, right, that's like saying we're going to shift this distribution over by x theta. So it's basically like saying our y is generated with a normal distribution parameterized by mean x theta and variance sigma squared from the z. Does that make sense? So like, if x theta was like 0, for example, then our points will lie on this line, this equals 0 line, and then perturbed a little bit by the variance. Now we're just saying we're going to add x theta to each one of them, so we're just shifting it over. That's like just like adding a mean. So, so yeah. So now that we're here, we can recall that each yi is normally distributed with this, with what I just talked about, right? This theta t xi mean and this sigma squared variance. Okay. Anyone have any questions on this part? Yep. So now this is just like a single data point. So we just, yeah, it's just like transposing. It's just like dot product basically. Yeah. Yep.
Wait, couldn't like there be multiple like parameters that like x? There's not just necessarily like one input like x, one x, right? There could be like multiple x. It's just like account for that.
Yeah. So x is a vector.
Okay, it is vector.
Yeah. Okay. So remembering that yi is normally distributed, so given in a normal distribution, right, we can find the probability of like a certain point in that normal distribution. That's what it kind of means, right? Like, if we go back to our graphic here, like, if we look at this blue curve, right, like points over here have low probability, but points over here have high probability. And that's given like by something called the Gaussian formula. I'm not going to talk about it a lot, but basically, I'm trying to find the probability of this point, right? So I can just plug it into the equation of a normal variable, of a normally distributed Gaussian. So this is what it is. I'm not going to explain it because I don't think I can. Someone just randomly came up with it, and it explains a lot of stuff in our world. Yep. Oh, it's because this is a vector and this is a vector, so you're taking a dot product. So this is not just like a single number; it's like a vector of numbers. So when you take the dot product, that's just like this is like our h theta. This is like our model. Yep.
But y in this case isn't necessarily just be like one output.
Yeah, it's an output. So we get some weird stuff looking like that. So like we want to optimize over theta, right? So none of this stuff contains theta. None of this contains theta. Only this contains theta, right? So what this turns into is we can remove all of this. We just get this. What's log e to the something? It's just this, right? And right, like this, all of this doesn't depend on theta. We can just drop that away. And then we have argmax of a negative thing. So we get argmin of this. So this is really cool, right? Like we proved like why this is the optimal loss function for linear regression with the assumptions that our data was, or our errors were normally distributed, independent, etc. Right? Like this is amazing. Like this is so cool when I first saw it. Anyone have any questions on this? Yep.
Where is this log coming from?
Oh yeah. So basically, like we're trying to take the max of this function, right? If you're trying to take the max of any function, right? Imagine the log of that function. Taking the max of the log of that function is equivalent to taking the max of that function because log is always increasing. So the max of the log of a function is going to be at the same point of the original function. The log just like doesn't disturb anything about the function, basically. Yep.
My question was on like the 1 over
Oh, this part?
Yeah.
Yeah.
Like, where does that whole formula come from?
This. Yeah. So this is like the part that. So this is like the PDF of a normal distribution. it just basically gives you, if you plug in a point here, it gives you the probability of that point in the distribution. Like the probability of the point in that normal distribution. So yeah, it's just some formula someone came up with. Yep. So we can get this in estimation. Yeah, the log turns the summation, the product into a summation. And then because it's a summation, we can like very easily drop irrelevant things and then get to this nice expression. Yep.
So is that why we just dropped it to?
Yeah. Like the minimum of something is going to be the same as the minimum of that thing over 2. Like, doesn't really matter. Yep. So yeah, like that's why we also drop like the variance of the noise. So like we don't really need to know that. It was just important to know that it was independent of each other. Okay, cool. So yeah, that's like, so this distribution only works if our data satisfy those assumptions. So let's talk about what happens if our data doesn't satisfy those assumptions. So for example, if the data is nonlinear, we can transform the variables. So we can square it, take the log of it, take the square root. We can try to find some sort of transformation that will make the data linear. So for example, if my data was like, e to the x, instead of just x versus y, it was e to the x versus y. If I take the log of that, then it'll become x versus y. So I can try and transform it to become linear. If the errors are not normal, like often this isn't too big of a problem, but transformations could help here. And yeah, I don't really know too much about that. But like maybe like you could use subsets of the data instead of using the whole data. And like outliers could contribute a lot to this issue, but typically like we don't deal with this too much. So like for example, like here's what I was talking about, right? Like if this like falls into like exponential distribution, so we can't fit a linear model of this. So instead of we just take the log of the miles per gallon and the log of like the explanatory predictor and explanatory variables, then we get this like really nice really nice like linear looking function. So now we can do like linear regression on this and like it'd be set. Okay, cool. Any questions so far? Any questions on anything covered in this entire lecture so far? Yep.
When you said regression is continuous.
Yeah.
And, when you're doing the probability, it's conditionally independent. Does that contradict?
No. So like this part, like the conditional independence it doesn't care like if this is discrete or continuous at all. Yeah. It just means that like I generated one sample and then I generated the next sample like without thinking about the first sample. Like if I use the first sample and somehow to generate the second sample, that means that it's not independent. Okay, so quick recap of this lecture. So we introduced linear regression. We used linear algebra to come up with a closed form solution that can easily give us, the exact formula that we're looking for. Yep.
Sorry, what was this closed form solution?
Oh yeah, just like a simple formula you can just plug everything into and you get an answer.
Okay,
So do you remember that xtx inverse xty? That was our closed form solution.
what's an example of something that's like you can't use a closed form?
Like gradient descent. Like gradient, like for example, if a huge neural network, like there's no closed form solution to that. So yeah, we use gradient descent. Or like for example, if you think like a simple example like logistic regression, you can't. There's no closed form solution to that. Yep. So like basically like when you take the derivative and set it equal to 0, you can't solve for that one theta thing that you're looking for. Then we use gradient descent to iteratively optimize the solution. So we don't use gradient descent for linear regression because there's a closed form solution, but it's important to introduce this concept because we'll be talking about it in the next lectures, and it's really like the building block of machine learning. So it's like really important to know. Okay. And then we also constructed a universe in which we could better understand our model and our assumptions behind it. And from that, we were able to see like a lot of where our assumptions and failures and drawbacks can come from. Okay, any questions? Okay, cool. So we're gonna do a 5-minute break, and I'm gonna have you fill out the attendance, which is this thing, and then while you do this, there's like a linear regression student notebook in the lecture 3 folder. So just make sure you can fire that up and like import the first cell, and if you can, like work on like figuring out what you need to install to get that to work, and also do this attendance. Okay, 5-minute break. Oh, yes.
What's the difference between the 3 ways?
That's like the not short version, so you can type that in or you can type that in.
Okay. What about the third
I have no idea.
one?
I just think let's use the second one. Hey. Okay. Just make like a usually like maybe need to make like a quick note about that. Maybe like
Trying to do like these things.
yeah,
I use content to run my program. So unless I do content install something,
yeah, I'll post those. And we're gonna like go through. But oh yeah, no, I say content. I'll post those. Yep. I just forgot to change it. It's like this week, so. Yep. So, like, basically, like, when we take a gradient, right, like, we need some input, like, we need an input to tell us, like, where our grade, what our loss function is, and in order to take this step, right? So, like, our loss function is defined by so we use it because it tells us what our loss function is, and we also differentiate it. So that's why we need a the reason we use multiple, like the reason in gradient descent we use multiple and average across them is because if you use multiple, that gives you a better estimate of where the true middle is. Does that kind of make sense? It's basically like think about like law of large numbers. One, you could have like be high variance. Okay? If you have a lot of variance, your estimate has a more confidence.
it's a different shirt. Like you change it.
Alright, so you said we use all of our videos. Yeah.
So, I was working on homework too, and for some reason, I did the pick3 install for both these libraries, and I'm still getting that it can't find the
Yeah, so it's probably because your Python, your like Jupyter Notebook Python isn't the same as your like the Python you referenced from the terminal.
Okay.
So one quick check to do is like you can just run like exclamation which space Python
Okay.
in here,
Okay.
and then in your terminal run which Python,
Okay.
and then it'll give you the paths for both of them, or like do
okay.
which Python 3, for instance.
Okay.
And then you should be able to compare and then figure out what's going on.
Okay. All right. Thank you.
For sure. Ew.
I was trying to finish up the homework, and I'm pretty much done, but I'm facing the problem here for the value, what's called the missing value imputation. Yeah, which I mean it affects this in 2 more blocks. I wanted to do it with KNN, with the KNN algorithm, but whenever I try to import, I'm trying to import like a library called Fancy,
Okay.
and it won't let me do it because it's filled with exit styles. And it just, if you just Google it, it seems like it's a nasty Windows right. I don't know if I can get it.
Yeah.
Like it did to me when I tried to actually install like Jupyter, but then somehow
Yeah.
I didn't install everything.
Okay, I'm not really sure. Could you make a Piazza post about this?
I did. I actually did.
Okay, we'll make sure to get back to you. We'll try and see what's going on.
But then just to finish the homework, should I just do something else?
Yeah, try and do something else. Yeah. Go. Yeah, I think this Okay, did everyone fill it out? Who has not filled it out? Put a thumbs down. Okay. All right. So who's? Can everyone open up the notebook and get to this page? Okay. All right, we're gonna get started. So, who is not on this notebook page right now? Okay, let's get started. So, everyone imported this. So, for this demo, we're gonna be looking at NBA salary data and doing some interesting linear regressions based on that. So, the CSV is in the directory, so you shouldn't need to worry about it. So if you run this command, what we're basically doing is we're using our standard pandas commands, which we have now successfully mastered since we've done both homework 1 and homework 2. We're going to import this CSV. We're going to drop that first column. We're going to drop any missing values. And then we're going to take a look at our data set to see what it looks like. So this is what we get, right? So has a bunch of like variables. So like wage, experience is one. And it's like games, minutes, whether they're a guard, forward, their assists, all-star, whatever, like even children. I don't even know why that's there. Like a bunch of variables, right? So we're going to be interested in like a few things. So we're going to try and predict their wage. We're going to try and predict their wage based on their experience and their points. So over here, I'm basically getting out, from this pandas data frame, I'm selecting their wage, their points, the experience column, and the log of the wage column, which we may not need, but we'll see. So is everyone here following with me? Okay, cool. So we have these. So basically, we've extracted all the information we need to know from the data frame. Okay, so we're going to do like a simple linear regression. So before we do linear regression, we should be able to plot. We should be able to plot and to see what our data looks like. So I've set up the plot here. I've included like the title and the labels and everything. We have our variables here. Can someone tell me what I should put in here to plot? Yep.
Plot that show.
Well, I haven't actually plotted anything here. Do you know like how I would go about plotting something? Yep. What dot plot? Okay, close enough. PLT dot plot, and then what should go here? Okay. Okay. So what is that? Yeah. Wage points, or I think it's points wage. Okay. So. Oh, oops. Wait, I think it's wage points. Wait, sorry? Oh. Oh, yeah. Oh, okay. All right, so hold on. Okay, so a little mistake. So what I tried to do is like tried to plot points versus wage, but they're not like sorted or anything, so it just turned out to be a big mess. So we're gonna do a scatter plot instead, and we're gonna just plot points and wage. We're not gonna do a plot, but okay. So that's what our scatter plot looks like, of points and wage. So yeah, like PLT.plot would like try and connect all these dots with a bunch of lines. That's what looked really weird. So we just want to point like where our dots are, like where our data is. So that's what it looks like. And how about for the other case, for the wage and experience? Someone shout it out. What are the arguments? Yeah, expert and wage, right? Okay, so this is our first plot. This is wage versus points. You can see it has sort of like a linear fashion. You know, there's like a lot of noise, a lot of errors, but we can see like some sort of linear trend. And this is wage versus experience. So can someone tell me why it looks like this? Why there are like these straight lines, seemingly straight lines? Yep.
Because their experience is like in years.
Yeah, exactly, right? So yeah, experience is in years. So you don't have like half a year or something like that. Okay. So now we're gonna do like a we're gonna fit a line to our data, and we're gonna plot it on this to see where it lies on our data. So just follow along with what I do. So we're gonna do my OLS for the points equals SM, which is our stats model thing that we use. Dot OLS wage points dot fit. So what we're doing here is we're constructing like a least squares regressor. We're passing it in our data, and now we're fitting it. So now this fit like creates like it fits a line to our data. And what we can do is do plt.plot points my OLS points dot predict points, and let's just say like color equals red. So now that I fit my model, I can predict using my training set, my points. And if I run that, I see this is what I get, right? So it's telling me like this is like the line that's like the best predictor of my data, or it's the best predictor of my wage versus points. And now I want to see like how the plot looks like for the second case. So I'm kind of lazy to typing, so I'll just copy this over, and I'll just change points to x per x per. Is everyone following me with me so far? Am I going too fast for anyone? Yes? Okay. Yep.
Is there anything wrong with like fitting our model with all our data and then predicting which?
Yeah. So this is what we talked about like last lecture a little bit briefly. It's like what we call like cross-validation. So typically, like we wanna why do we construct a model, right? It's to be able to see like how well it'll do on like new data points. So like the new incoming data, we can evaluate what their output is. If we just evaluate on our labeled data, we already have the inputs and the outputs. We don't really need a model, right? So the whole point is to see how well it generalizes on new data points. So if we test on stuff it's already seen, then that's kind of like a biased way of testing it. It's like you've constructed this model to best fit this data, and now like the measure you're using is like this data that it's already seen. So like it's the same reason like your tests are like not the same as the homework questions, because you've already seen that and you know how to do that. So you can like overfit to that in a sense, right? So that's why we use like held out data to like report our test error. Okay, so once we run this, we should be able to see. Oh god. Oh.
Points, third line. You left it as points instead of first parameter. Plot points.
Oh, yeah. Wait. No. Right. Okay. Right, so yeah, this is like, they look pretty similar, right? Like the lines look pretty similar. So yeah, we'll be able to see like which one is a better predictor. And like just to note, like just because one line has a higher slope than another, doesn't mean one line is better than another. Like some people, like sometimes like that could be like a misconception, like like the stronger your slope is, like the better of a predictor it is, but that's not necessarily true, because your data could be normalized in different fashions, or like your data could have different shapes. So like the slope of the line doesn't really say anything about like how good the model is. Yeah, question? Yeah. Okay, so now we're gonna do some. We looked at this. We want to figure out what is actually better. So let's do some like cross validation. So we have our wage, points, and experience. We're gonna split it up into train and validation sets, or train and test sets. Okay. So now we're gonna do a bit of regression on these points. So it's like pretty much the same code that we had before. So I'm just gonna copy that. So we're gonna predict, but instead of our let's just say my OLS this time, right? And we want to predict on our points train, not all our points, and our wage train. And now that we fit on our trading data, we want to figure out our new like predictions for our wage hat. So we do my OLS dot predict points valid. So I train on only the training data, and I'm predicting on my validation data. And now I have my wage hat, and I want to compare it to my wage valid. So an easy way to do that is the L2 norm, or the Euclidean distance, which I was talking about in that matrix notation slide I had. So that's just np.linalg.norm wage valid minus wage hat. And then norm gets the Euclidean distance, which is like the square root of all that. But I don't want the square root. I want like just the sum of the squares. So I'll square it, and then I'll divide by ln of wage valid. Oops. So this is what I get, right? I get the MSE for my model is like 0.448. Okay. So at this point, like, this doesn't really mean anything too much to me because, I mean, this tells me like, on average, how much wage am I off by? But we don't really have anything to compare it against. So let's build our second model. Is everyone done typing this part?
Is this going online?
Yeah, I'll post the solutions up later. But yeah, if you can, you should try and type this along with me so you can see. Okay, so now like for the second one, I'm gonna do like exactly the same thing. So I'll just like change the variables. So instead of points train, I have expert train, and instead of points valid, I have expert valid. I think that should be it. And now I see that my MSE is 0.55. So right off the bat, like, can you tell me which model is better? Experience? Who said experience? Why do you think experience is better?
I'm not gonna say.
No, that's okay. So, like, be careful, like, not to interpret this with accuracy, right? So it's not like our model's like 55% accurate. This is like our mean squared error. This is like, you know, the squares of the error is how far away it was. So a larger value, like a larger loss, means that your model is less accurate. So, you know, the first one is better. So what that means is that points is a better predictor of your wage than experience is. Does everyone follow with that conclusion? Okay, cool. So yeah, conclusion is points is a better predictor. So now you remember here we're just doing a regression on one predictor variable. But you remember in our formulation we had multiple predictor variables. So let's go ahead and do that, right? We don't want to do just experience or just points. Let's do both. So here we do multiple linear regression. So our data now includes experience and points. And typically, so I'm going to go ahead and add a constant here. That's the same thing you saw as like adding that bias term. If I add a constant, I can like add in that y-intercept, that bias term. And then I'm going to fit my model on the wage in like both the experience and the points. And I have this nice utility that I can do like dot summary, right? So this will like give me a summary of my model. So it does this and it gives you like a bunch of random stuff about like most of it I don't understand, but you can look here, right? You can see, you can find the coefficients of your model. So my y-intercept is this, or my bias is this. This is the coefficient for experience. This is the coefficient for points, right? So it tells you like what your model is, and then it tells you like the error, like the standard errors, some like p-norm, chi-squared tests. I don't really know. I failed AP stats. Okay. All right. So it does this for you, right? So now we've constructed our model. So it's hard to visualize it in like 3 dimensions. So this code will do that for us. So just run it. And it'll show us this, right? So what this is this axis here is experience. And this axis here is points. And then all our data lies in this like 3-dimensional cube, right? And this is our plane. So instead of a line in 3 dimensions, now we have a plane, like a hyperplane. In 3 dimensions is a plane, but in the more dimensions we go in, and greater than 3, it's called a hyperplane. So just some like linear function, right? And it tells us like how it's dividing up the points, or like where our predictions lie. So for example, here this is the wage, right? So as we increase more experience and points, we get a higher wage. And same thing, the lower experience and the points we have, lower wage. Does this make sense to everyone? Yep.
So the constant was added with the API.
Yeah, with the API. Yeah. It's just like add constant. Yeah. Yep.
Wait, so like we went back and we're no longer separating our training and testing.
Like I mean, we could do that, but there's no model to compare against. Like we're testing on both variables, so yeah. Okay, so So in the beginning of the lecture, someone asked me, I think in the back, our model was just coefficients times, our predictor variables. But what if those predictor variables were of higher degree, right? What if we didn't want just like a, theta p xp? What if we wanted theta p x squared or something like that? So that's what we call polynomial regression. And so let's introduce it softly, right? So far we have our data with these two independent variables, right? So let's call them alpha 1 and alpha 2. Change of notation, right? Let's call our experience and experience and points alpha 1, alpha 2. So far our models have looked like this, right? We have theta 1 times alpha 1, theta 2 times alpha 2, plus some theta 0 offset. Everyone follow here? Okay, cool. So now the question is, what if our features, what if we didn't want it to be just the variables? What if we wanted to do something hella fancy, right? Like what if we wanted to do theta 1 alpha 1 squared, theta 2 times theta 2 times alpha 2 times alpha 1. Like what if we want to mix it up, So we can do this, and it's still linear regression. Why is it linear regression? Because these coefficients are still degree 1. So it's still linear regression. And in fact, we can do crazy stuff like this very easily with something called polynomial features. So like every polynomial has a degree, right? And this degree controls to what exponent or what order these items are multiplied or raised to the power. So what we've been doing so far is really polynomial regression with degree 1. That means each of the explanatory variables here was just raised to the degree 1. Okay. Now what if we wanted to do degree 2? That's what this is, right? We're finding all the ways to combine these explanatory variables that'll give us a degree 2 or fewer, right? So we have here this theta 3 times alpha 1 squared, which is degree 2. Theta 4 times alpha 2 squared, which is degree 2. And then theta 5 times alpha 1 times alpha 2, which is still a second degree in in the degree of the independent features or the predictor features. And of course, we still have our lower degree features, our 1 degree features and our 0 degree features. So you can imagine, we don't just want, we can't just, we can do this for more than just degree 2. We can do degree 3, degree 4, and the amount of cross terms will increase exponentially or something like that. But this is still possible, and this is still linear regression. This is still polynomial. Polynomial regression is a type of linear regression, and it's linear because all our coefficients are still only to the first power. So this way we can get we can extract more information out of our predictor variables. We can find new relationships. For example, previously there was no way to find a multiplicative relationship between alpha 1 and alpha 2. Now we can do something like that, right? Yep.
What's a situation with pi, I guess?
For example, if you're trying to fit a polynomial, if you suppose you had a scalar x and a scalar y, and your true model generated x by with the polynomial x cubed, right? There's no way observing just those x you could fit a linear model. But suppose you took every x and you cubed it. Now you can fit a linear model really easily, right?
And that still counts as linear regression.
Yeah,
It's just constant multiplied by whatever.
Exactly. Our coefficient is still degree 1. So what happens is that if we plot it, right, it might not look linear because, for example, x cubed might look like this, curvy. So it might not look linear, but we're still regressing on degree 1 coefficients, and that's what's important. So it's still linear regression. So this is one reason why it's so powerful. You can still get non-linear boundaries or non-linear regressor functions with linear regression by doing polynomial features or kernels, which we'll talk about in a few weeks, or something else of the sort. Yep. That's non-linear regression or least squares. So yeah, there's that's a very open problem too. So you can definitely do theta 4 squared or something like that and try and optimize over that. But now there's no closed form solution. So what do? Gradient descent, right? Yep. So yeah, so there is a thing called nonlinear least squares, and you use gradient descent to optimize it. Okay, so let's do polynomial regression on this, right? So let us see. Okay, yeah. So here we want to add our bias to the data set. So here I'm just gonna do like x equals sm dot add constant x, and then so this is just adding a constant to the data set, and then I'm doing so this data is still like only of degree 1, so I want to make it in all these cross terms of degree 2. So I can do that easily by doing poly equals polynomial features degree. So this will take constructs like a variable that can now augment my data. So now I just have to do x equals polyfeats dot fit transform x. Does everyone follow so far on what I did here? So here I added the constant. Here I create like a polynomial featurizer of a certain degree, and now I'm like transforming this x. I'm fitting it and I'm transforming it. Okay, I think that's all the code you need to do here. Okay, yep. So just the rest of the code here, I'm taking my data and I'm splitting it into a training set and a validation set. So make sure to do this, pretty important. And now you can fit your regressive model, same way we did before. And now I'm just printing out a bunch of like what the degree was, what the training mean squared error was, the validation mean squared error was. Okay? Anyone have any questions on like this provided code? Yep. Pardon? Oh yeah. This part? Yep.
What exactly does polynomial features do?
So this is just like a class, and basically given like some data, it'll compute all the cross terms to a certain degree.
Okay.
Yeah. Does that make sense? Okay. Yep.
How did you decide to split?
So this is my split index. So I'm just using 80%. So 80% train, 20% validation. So I'm just using like how many data points I have, 80% of that, making that an integer so it's a valid index, and then use Python splicing to.
And shape returns what exactly?
It returns like a tuple of like all the dimensions. So the first dimension would be the number of data points. Yep. Okay, so I can run that, and basically what I'm doing here is I'm looping through all the degrees up to degree 5, and I'm basically doing the regression and then storing the MSEs for both the train and the validation. So I've already set this up, so this is pretty simple. Yeah, so now it like tells us like what all the MSEs are. And now I can plot it using this plotting functionality, and it tells me this. So train is the blue, and red is the validation. So right off the bat, what can someone tell me about looking at this plot? Think about cross-validation, training data, overfitting, bias, variance, etc. Yep, no?
It was like, is there better on the validation data than the training? Well, it's the mean square error on the last.
Yeah, but I think I just didn't normalize by how many data points there are. So, but like, ignoring that little fact. Yep.
As your degree polynomial gets larger, then the mean square error gets less. So that's essentially like.
Yeah, exactly, right? Okay, so this is a very key concept, right? Like, as my degree increases, my training accuracy always decreases. So as my model gets more complex, my training accuracy always decreases. Why? I mean, my training accuracy always increases. My loss always decreases. Why? Yeah. Pardon? Yeah. Yeah, this is overfitting, but why is it overfitting?
Because we're trying to fit more complex
Right, so wouldn't fitting a more complex one lead to more error in your estimate? Wouldn't fitting a more complex decision boundary lead to more error?
More error in what?
More error?
Oh,
More MSE? Yeah.
But I mean, because we can fit what, by increasing the degree, whatever kind of we want.
Right. Yeah, right, exactly, right? So what he's saying is that we can make the coefficients whatever we want. So if it turns out that degree 5 coefficients aren't useful, that's fine. Just set those coefficients to 0 over there. And now our model becomes degree 4. Right? Just like zero it out, so it doesn't matter anymore. Turns out not to be useful, don't include it. So that's why you can see it kind of plateau. Maybe like if found that degree 5 wasn't as useful, right? So our training accuracy will always get lower because if we add more complex stuff to our model, it can always zero it out and not consider it. But now, as you can see that this training error is dropping, my validation drops at first and then increases, right? So when my validation starts to increase, that's the sign of overfitting. That means my model is generalizing less and less. So when it's dropping, that means it's doing better on unseen data. When it starts to increase, that means it's not as good as generalizing, right? So at this point here, my model starts to overfit. And the reason is because it's so complex, it's able to fit the really small noise measurements in our data. So instead of fitting the linear model that we talked about that generated the process, it starts to fit those E's, those errors, that noise. And that's what overfitting is. That increase in noise means that our model has more variance because it's like, you can think about it like really small like squiggly decision boundaries that fit all this like random noise rather than this like linear thing that we want. And so that's why it's always important to like use cross-validation and figure out what exactly your best model is. Because having a high degree polynomial, having the most complex model isn't always the best. Because it can overfit. And it overfits because complexity can easily capture noise in the data. Simple, like this is a linear regression, so this isn't as bad. Because you know, how much noise can you capture with like a line, you know, it's like very small. But like the more complex your model becomes, overfitting becomes a really big problem. And so keeping this in mind is key. Because if you look at your training data, it's always going to decrease. So you never know when you overfit unless you validate. Anyone have any questions on that? Going once, going twice. Okay, lecture's over. Thanks for coming, guys.